Good afternoon, everybody, and thank you very much for finding the courage to be here after one intense week of talks. On the bright side, I've got a full set of pictures in my talk, so it should be easy. On the not so bright side is that you will have to wait for me to conclude. Speaking of pictures, I hope everybody knows where London is. Last time I checked, it was still in Europe. It will be there for a couple of months. I don't know what happens next. This is where we are, University College London. Great area if you want to go to the British Museum, if you want to go some shopping. And fun fact about UCL, we are the largest university in London, the third oldest in the UK, and we are widely renowned for being the place that awarded Arne Wickenbroek his PhD diploma. So I'm particularly proud of that. We have also the unofficial record of being the university with the shortest distance to 4 on the main train and tube stations in London. And if you look underground, and in case you're asking, we are in the basement, we have a laboratory. We're sitting exactly on top of 3 of those lines and very close to the others. The bottom line of the story is that this is the last place on Earth, probably, where you want to do some atomic magnetometry. And good for us. And since we were not happy, we decided to do that in an unshielded environment. And the reason is, why do things more easily? Let's complicate things. And, well, we succeeded. And actually, following an idea we had back in 2013, 2014, of using atomic magnetometers for performing magnetic induction tomography, we obtained images like this. And I hope this is familiar to someone in the audience, because this was obtained with the contribution of Arne when he was still a postdoc in my group before moving here and becoming a big boss. After he left, however, we said, okay, we're sorry, but we need to go on. So we redesigned completely the experiment, and in the next few slides I will show you what we have been doing after Arne left. I would also like to add, it's particularly proud for me to learn in this conference that many other groups now are working along the same lines. We heard a very nice talk from Caspar Jensen yesterday. We heard a very nice talk from Vitold from National Physical Laboratory earlier today. And I've also heard that Strathclyde with Stuart Ingleby may be interested in looking into that. So what we've done after this is that the idea, people have already described this, so we'll be brief. We have an oscillating primary field, magnetic field, radio frequency. This induces eddy currents in an object, and we want to detect the response of this object. So contrary to other techniques we've been hearing about in these days, this is intrinsically active. And the key of all of these is that, as you can see, it depends on the electric properties of the object and also scales with the frequency. So the idea is that if you can move your sensor across the object, or the object with respect to the sensor, you can produce a map of the electric properties, mostly conductivity, of your target. The problem is, this is as good as your sensor. So if you use a very poor sensor for detecting secondary fields, you're not going anywhere. And this is the rationale for using atomic magnetometers. So in 2016, we demonstrated for the first time that this approach could be done with a radio frequency atomic magnetometer. I won't dare to say anything about this to this audience. You know much better than me what's going on here. Let it suffice that the same RF field which drives the magnetometer is here used for inducing eddy currents. This allows us to use a lock-in amplifier, and as I said, whilst moving the target of the sensor with respect to each other, we could obtain images like this. This is obtained as everything I will show you today in a shielded environment, and these are just raw data plotted in a color scale matrix. In this case, you can see a crack in an aluminium ring, which was great for us, but it was sort of easy. It's 10 to 7 Siemens per meter, so it's a very big signal. So what I'm going to say now is that we tried to develop a better sensor, a better technique, and whilst we're doing this, some possible applications came into play, and I will show you some of these. One example is this, and I think this was mentioned in Stuart's talk earlier. So security screening is an open challenge, and many situations standard metal detectors are challenged, they cannot penetrate conductive barriers, and they have limited resolution. At the opposite side, X-rays are not really portable, they're not safe to use, you can't shine them on cargo containers, especially if you suspect that there are stowaways. So in collaboration with the UK Department for Transport, we realized a set of demonstration, and in this case you can see that by exploiting the skin depth, and namely by lowering the frequency of the primary field, you can penetrate several barriers which are conductive. You can see here an object, this is a copper disc, again an easy target, concealed by 2 mm aluminium shield and also by a composition of 2 mm aluminium and 2.5 ferromagnetic steel shield. This is also the case where we introduced a technique we have perfected in years, which is an automatic compensation of stray fields, which allows us to do the imaging and to perform operation of atomic magnetometer whilst being close to a ferromagnetic target. I don't have time to discuss the details, but I hope I give you the idea. We were lucky enough to be featured on BBC News, and we have recently commissioned our third generation of portable scanner. This is handheld, that can be placed also on a 2D or 3D scanner. It comprises everything, including the laser sources. So what you see here is just extraction of the signal and power cable for the system. The characterization of this is in progress, so I can't tell you much more than that, but we're quite proud of this. Moving forward, another kind of application is underwater detection for early surveillance. We don't want to find submarines because that is done already with a number of technologies, but there are areas, for example, shallow water, where acoustic methods, sonar, are challenged because of the echo coming from the seabed. So you can't place a sonar basically in a harbour. You won't see anything. So again, together with the Department for Transport and the STL, which is a defence-related laboratory in the UK, we developed a few demonstrations. This is a proof of concept 2x2 planar array of 4 radiofrequency atomic magnetometer, demonstrating active tracking and detection of an aluminium target moving underwater. And we also went to a floater quarry by realizing a, so to speak, portable version of the system, and we were able to detect a cylinder of aluminium. I can't speak about the characteristics of this system, but I can give you an idea of how big was this at the bottom of the quarry. And as you can see here from these traces, even when the target was literally at the bottom of the quarry, 10 meters underwater and 11 meters from our system, we could detect its position when we were driving on top of it. It's a case where, as we heard earlier, the 50 Hz noise was virtually absent, but there was wind, rain, and all these sorts of things, not to mention a very unstable floating platform, which almost made me seasick. So we had other problems to face. This is, of course, a proof of concept, but it's something that it can be done. And it's worth noting that there's no countermeasure for this. So you can degauss your object and make it invisible to purely magnetic detection. Since our detection is active, as long as the object you're looking for is more conductive than seawater, we will see a signal. Vetoed earlier from MPL, this is work we've done in collaboration with them, show us results from what we call non-destructive evaluation. So I won't spend too many words on this. I will just say that this is done with a conventional, let's say, radiofrequency magnetometer, not with the spin maser Vito told us about earlier. The interesting thing is that we obtained 30 centimeters liftoff from the recess, and we got a sensitivity in thickness of 0.1 millimeters, which means that you can go to your company, oil and gas industry, and say, okay, in this pipeline, you had in the last 6 months a thinning of 0.5 millimeters. You want to have a look at that before a spillage or a serious damage happens. And it's worth noting again that this is done with ferromagnetic carbon steel. Moving on, while we were improving our system, we said, why don't we try to do some material characterization for technologically relevant or interesting materials? We gave it a go. This is an arsenic-doped silicon wafer, standard in semiconductor industry. This is doped with arsenic, and it's 625 microns thin. You can see here a photograph of a fraction of the disk, and this is the image obtained with our system while scanning this object with respect to the magnetometer. And as you can see, there's a very well definition and reproduction of the system. Bear in mind that the doping in this case is homogeneous, or at least this is what we were taught by the company. So this effect you see here is just because of the boundary. More probably interesting, we also demonstrated that by varying the frequency and where you perform your imaging, you can extract data and behavior about the materials, and therefore you can classify and distinguish among different populations of materials, which is in principle interesting, but of course, before being actually useful, you need to improve some things, for example, the spatial resolution. This is very interesting, however, because you don't need any contact or ohmic circuits to be built on top of your wafer, so it's completely non-destructive and non-invasive. So speaking of improving spatial resolution, we follow two approaches. By the way, I know I shouldn't talk about MV centers, but one way of doing that is using an MV center sensor for performing this, and this is something that Anne Wickenbrock have investigated in this group. I think recently, a few months ago, there was a paper for that. But if you want to keep to atoms, or to stick with atoms, what you can do is to apply some machine learning. And we achieved sub-pixel resolution with a relatively small amount of images for training, and also shape recognition and other characteristics of the system. This also implies that our system had to work 24/7 for several weeks with uniform and continuous performance, so it was a technical challenge for us to achieve that, especially if a few 100,000 of people are coming out of the train stations in the area, and there are at least one train per minute. The other possibility is to use cold atoms. So you're exploiting the control you have with cold atoms to make your sensor smaller and to move it around your object. This is a work in progress. We recently demonstrated in our subdoppler cooled 87 rubidium an RF pulse magnetometer. Our next step will be moving to our Bose-Einstein condensate available in our lab. And this brings me to something that, and I'm grateful to him, Caspar mentioned yesterday, because since our sensor is becoming better, we say, okay, let's make things more and more complicated. And the idea is to do biomedical imaging with this. We have possible applications in many fields, but we have a specific applications in mind, which is atrial fibrillation. I will spare the gruesome detail, but this is a normal heart. You have a polarization wave propagating and forcing the heart to contract and relax at the right time. About 10 people in this room, by the time they reach the age of 65, will experience this. So a turbulent random activity in the atria, which will be manifested with shortness of breath, sense of tiredness. It's fine. The problem is that this increases your risk of stroke by 60%, and it costs a lot in terms of money for the healthcare system and, of course, for people. The problem is, doctors don't know how to diagnose this unless you are admitted to the emergency department with this situation, and may be too late. Even more importantly, when drugs are not working for solving this problem, surgery is the only option. The problem is that surgery is currently done blindly. They don't know which part of your heart is not working properly. So here's the hypothesis. This rotational activity is caused by a permanent change in the heart's conductivity. Imagine this like a short circuit in your heart. So instead of propagating polarization, there's a current discharging locally and creating this problem. This is what they call arrhythmogenic faulty, which is what we would like to see, because if this is a change in conductivity, then if we build an instrument to map conductivity of the heart, we can tell them, okay, we have a way of diagnosing this before the crisis is ongoing. You have a way to guide your surgery, and you could ideally implement large-scale epidemiologic studies. So we recently realized this system, which is really not portable. The laser table is in this way. But this allows us to operate at high sensitivity regime up to 7 megahertz. We're normally working around room temperature, but ideally we can scale it up to 65 degrees. We're usually working with 85 and 87 rubidium, but we can change the chamber which is contained in here. And this black part here is also the flat gauge we're using for background compensation and monitoring of the fields. And with these, we've obtained these images, which may be not particularly exciting for you, but again, they were obtained without any background subtraction, without any averaging, just like this. And these are semiconductors wafer doped to get 50 Siemens per meter. And these are as good as they come out from our instrument. The volume is rather small, and we have a resolution of 2.5 times. The reason we reached 50 is because when we asked the company to manufacture a silicon wafer below 50 Siemens per meter, they basically reply, you guys are crazy. So we needed to stop here. But interestingly, we had to develop a trick, so to speak, to reach this. And the trick is the following. If you're measuring where the phase gradient is maximum, which is what would you like to do normally, you get this, which is not really an image. And the reason is your noise is very big, because more change in the magnetic field obviously causes a big change in phase. And since you want to identify a few degrees, you need to make this stable. So the idea is that you have a very sensitive magnetometer and then you bias it to work where the gradient is smaller. And then, believe it or not, this is the same 50 Siemens per meter sample, imaging in the two different positions, here and here. And then, by magic, so to speak, you obtain this image. And if you plug these numbers into our model, this is the objects we imaged, this is the biomedical range, this is our projected sensitivity at 5 megahertz. So basically, we can say that we met the requirements for unshielded biomedical imaging. And since we're there, we said, okay, let's have a look what we can do before we upgrade the electronics to operate up to 7 megahertz. Ask a chemistry people, they say acids are the best options for controlling the conductivity. We didn't want to have HCl on top of our sensor, so we use sodium chloride in deionized water. And these are preliminary, they literally come in as we speak, so I apologize for the poor quality of the presentation. But this is saline water in a petri dish. You see here the external diameter of the dish, 4.3 millimeters, and these are imaged at 4 millimeters depth. So 1 pixel here is 4 millimeters. There's also a triangle. There's something to do about it, but it still works. And speaking of last-minute additions, this is 25 Siemens per meter, and these, as you can note, the different color scale, we didn't have literally time to change it. It arrived 5 minutes before I uploaded the presentation here, is 15 Siemens per meter. So the goal now is to explore this, see where we can go, and then make a demonstrator out of it. We are already collaborating with cardiovascular engineering and cardiovascular science at UCL, and with this we hope we can get preliminary data which will be fed then in a clinical study to validate our technology. In conclusion, I hope I gave you an idea that it is relevant or interesting to explore a different approach to the use of atomic magnetometry, and also that we are finally able to fulfill our dream or our idea of a few years ago. With this, I thank especially Ferruccio, Renzoni and Cameron Dienz and the members of our group, and of course I thank you for your kind attention.